Hi everyone, I am Sagar Sudhakara, PhD student at University of Southern California and co-author of Optimal Communication and Control Strategies for a Multi-Agent System in the Presence of an Adversary paper. So the introduction of the paper is that we we are dealing with interaction between cooperative agents in team and adversary. So this is a figure wherein there are two agents and there's an adversary. We are dealing with interaction between those agents in the team and the adversary. So agents in the team have different information, but have the ability to decide when to communicate. So the goal is to find the best communication and control strategy for the agents in the team. So the outline of the presentation is that first we're going to discuss the system model. Then moving on, we discuss about the information structure and decision strategies. We discuss the preliminary results and reduced private information. And then we provide a common information belief-based dynamic program solution. And then later on, we discuss some special cases and extension to our problem. So the system model, we have a global system with state x0t and two agents with their local state x1t and x2t respectively. And information can be exchanged between both the agents. That's denoted by zxt. And there's an adversary whose control action can influence the global system. So the joint action UT is provided by U1T, U2T, and the adversary action by UAT. And the dynamics of the global state is affected by the action of the adversary. And the dynamics of the local state of agent I, get denoted by xit plus 1, is influenced by the global state, the local state of that particular agent, and the control action of that agent. Now, the communication protocol is that agents can dynamically decide when to exchange the local state information. Either of these agents can initiate the communication. Communication action MIT by agent I at time t is given by this particular MIT, which is 1 if agent I initiates communication. If it doesn't initiate any communication, it is 0. It's a binary variable. Similarly for the other agent. And information exchange between these agents. So if MIT is 1 and if the information is exchanged between that agents, that ZXT is x1, 2t. So if the communication is initiated, the local states of the agents are shared between them. Otherwise, it is just none. And the adversary observation is a noisy observation of the information exchange between the observation. That is noisy observation of ZXT. So we follow this particular information structure. So there's a action and observation timeline. That is at particular time t, we observe the communication action is taken and we observe the information exchange between those two agents. And even adversary obtains a noisy observation of the exchange information. At time t plus, control actions of the agents and control action of the adversary is taken. Again at t plus 1, the communication actions and the communication observations by both the agents and the adversary are seen. So this repeats. So using this particular action observation timeline, we provide the information structure at both time t and t plus. So before communication decisions are made, the information available at adversary is denoted by IAT. It's nothing but the history of global states, communication actions, adversaries action, and observation. And the agent I information at time t is nothing but the adversary information, plus we have this local state history of the local states of both the of that particular agent I, history of the control action of that agent I, and the information exchange between both the agents, included along with the adversary information. So now once the communication decisions are made, the information available at time t plus for the adversary is denoted by IAT plus, and it's nothing but the adversary information at time t, IAT, comma, the communication action and the adversary observation. Similarly for agent I at time t plus, the information structure is IAT plus is nothing but IAT, the information available till time t, plus the communication actions and the communication observations. Now coming to the decision strategies and strategy optimization problem, we deal with randomized decision strategies. The communication strategy is denoted by FIT and MIT is a communication action sampled from the distribution FIT on the information structure at time t for that agent. So Communication strategy is given by this particular equation. The control strategy by GIT, I8 on IIT plus, and the adversary strategy is this GAT on IIT plus. So these actions are sampled from this particular distributions. Now coming to the total system cost. So we have two components in our system cost. One is the control cost, which is dependent on the states, the actions, and the action of the adversary, plus a state-dependent communication cost, which is denoted by rho of xt. And this communication cost is only incurred when the communication is initiated by either of these agents. So that is the total system cost. So the team aims to jointly minimize this system cost while adversary aims to maximize the total expected cost. So this min-max optimization problem is now a zero-sum game between team and adversary, which is denoted by game of G. So the min-max value of this game G is given by SUG, which is minimizing over the strategy F comma G and maximizing over GA, G of F comma G comma G. So to solve this min-max optimization problem, we are trying to divide our information structure into different components. The first component is the common information component, which is information available to both agents and adversary. So at time t, the common information CT is given by IIT, and at time t plus, the common information CT plus is nothing but the adversary information at time t plus. That's IIT plus. So the increment in common information at time t plus, ZT plus denotes the increment in common information, that is CT plus minus the CT set, which is nothing but the adversary adversary observation and the communication actions M1 comma 2t. And at time t plus 1, the increment in common information ZT plus 1 is nothing but the set CT plus 1 minus CT plus, which is nothing but X0T plus 1 and UAT. Similarly, private information, that is information available only to the ith agent, that is denoted by PIT. That is nothing but IIT minus the CT set, which is nothing but the local states of that agent I, the local history of the control actions of agent I, and the information exchange between both the agents. And at time t plus, PIT plus is again all the state variables of that particular agent I, all the control actions of that agent I, and the information exchange till time t. Now we bring in a new variable called as dt. dt is the common information between both the agents, and at time t it's nothing but p1t intersection p2t. There is nothing but the information exchange between both the agents till time t. Similarly, at t plus, the common information between both the agents is nothing but the information exchanged between both the agents till that time, which is zx1 to t. So now the team's common information is ct comma dt at time t and ct plus comma dt plus at time t plus. So given this team common information ct comma dt, the two agents local state and control actions are conditionally independent. So the two agents local state at time t and time t plus local states and control action, when conditioned on that team's common information at that particular time instance, then they're conditionally independent. So we have this conditional independence property lemma. Now coming to private information reduction, recall that agent's I strategy was dependent on IIT and IIT plus. So we had this particular agent I strategy. Now we are going to consider a class of reduced private information strategies denoted by J red, which is of the form just xit ct comma dt. We are able to ignore xi1 to t minus 1 and ui1 to t minus 1 in both the strategies. So we have a lemma where we can show that agents can be restricted to reduced private information strategy without change in the min-max value. So the min-max value of the original game and the reduced private information strategy remains the same. So to solve the min-max optimization problem, we are going to provide a virtual game. So in the virtual game, there's a virtual player denoted by VP team overseeing both the agents 1 and 2. At time t, VP team selects the prescription gamma 1T and gamma 2T, which maps agent's private information to distribution over communication distance. And this agent side communication decision MIT is distributed according to this particular equation. And at time t plus, VP team selects prescription lambda 1T and lambda 2T, which maps agent's private information to distribution over control decision space. So now agent side control decision UIT is distributed according to this particular equation. So now adversary selects distribution gamma 80 over its action space, and UAT is sampled from distribution gamma 80. So now this virtual game G is nothing but a zero-sum game between virtual player and an adversary. So this virtual player is overseeing these two agents. Now at time T, VP team selects its prescription according to a control law, kite team T. And this prescription gamma T is nothing but kite team T of CT comma past prescription. So CT comma past prescriptions were the information available to the virtual player at time T. So we apply this control law over CT comma past prescriptions to obtain the prescription gamma T. Similarly at T plus, we obtain the prescription lambda T by applying the control law chi team T plus on CT plus comma past prescription. And adversary obtains its prescription. Adversary selects its distribution according to the control law chi A T plus, which is applied on CT plus comma all its past prescriptions gamma A 1 to T. So now the total cost associated with the strategy profile chi team and chi A is given by this J of chi team comma chi A, wherein the cost functions remain the same. So now the important theorem which connects the original game to the virtual game is that the min-max value of the original game and virtual games are identical. That is, we have the same min-max of J equal to the min-max over this chi team comma chi A strategies. So once we connect the original game to the virtual game, we try to provide a solution using the common information belief-based dynamic program. So in the common information belief at time t, the belief is denoted by pi t, which is a belief on xt comma dt condition on the virtual player team information, that is ct comma past prescriptions. And similarly at t plus, pi t plus is the belief on xt plus comma dt plus condition on the vp team information at t plus, that is ct plus comma past prescriptions. So now VP team can find its min-max strategy by solving the following dynamic program. At t plus 1, the value function is 0, and at t plus, the cost to go function is given by this particular equation, and the value function at t plus is given by this equation number 1. Similarly, at t, the cost to go function and value function is provided by this particular equation number 2. So once we provide the dynamic program, it can be solved using any well-known methods. Once we deal with the DP, we get into some special cases and extension. One of the special case is that if adversary sees the message perfectly. So the adversary observation is now ZXT and not a noisy observation of ZXT. Then the private information of agent I, T and T plus is XIT. So because of that, prescription space is now substantially smaller, and we have a smaller belief space and a simpler belief update. And one extension to our problem is that if adversary can interfere with communication, what if there is a failure if P maps global state to failure probability, and failure probability is given by P of X, where X is the global state, then the ZXT is now Z error T. That is, even if communication is initiated, only with probability 1 minus P of X, Z error T is now X1 comma 2T. Otherwise, it is the null. So even with that particular model, all our key results hold. The private information reduction lemma holds, the virtual game dynamic program still gives us the min-max value. So the conclusion of our paper is that zero-sum game between team of two agents and a malicious agent is discussed. Agents can strategically decide at each time whether to share their private information with each other or not. We characterized the min-max control and communication strategy for the team using a common information belief-based dynamic program. We prove that agents in the team can ignore a large part of their private information without losing optimality, and reduction in private information substantially simplified our dynamic program, which in turn improves the computational tracking. Thank you.